like to thank Dr. Keelan for adding this. I did not put that in there, but it looks nice. So, all right. So we're going to talk about how to make these spin-polarized spectra. So after doing previous calculations, let's assume that you've already done the spin-polarized density of state. Remember, you have two different lists of state, lists of the states. You should also have a wavecar and an outcar file. Again, it's helpful to make a new directory that's labeled, the model that you're working with, along with spectra, just to help organize things. You'll want to inspect the outcar, and you'll want to find those two lists of states and see how many levels there are. They both should have the same number of states, but they might not be populated the same. You also want to create a file called input overlap. These are weird symbols. It's supposed to be the return arrow. So 3 lines. The first line should just be 1. The third line should be as well. The second one will be the number of states. And if I remember correctly for the system that I was working with later on, it's something like 46. But if you have a lot more ions in your system, you will have more spin states. So the first code that you'll want to run is from the bin. You'll want to extract the energy populations. And this is sort of, I think it's the same as the energy states that Caitlin talked about in her presentation, but there is a program that does it. You will want to look at it. And this is just for, I think this is just for the first one. But it actually does, it does both systems. You'll have energy pop and energy pop down. And with a lot of these programs, the spin up system will just look like it has any other name that you've seen before. But the down system has that down add at the end. So energy pop is just the spin up system. Energy pop down is the spin down. And as I said before, the highest occupied and lowest unoccupied of these two systems are not necessarily the same. The second code that you'll want to run is the OS dipole spin up. And this will create the oscillator strength. And it has all kinds of transitions. It'll simply take every state and it will calculate the difference between that state and every other state that's higher than it. So you'll have transitions that are from an occupied state to an occupied state, so 1 to 1. You'll see this later on. You'll also see 1 to 0, which is what you're interested in because it's an electron moving to an empty energy level. And then you'll also have an unoccupied state moving to another unoccupied state. And if you actually open it up and look at the file, I think it's the next slide, I'll have an example of this, but there will be 2 columns, a bunch of 1s and 0s in the first one, and then the second one is also. And the one that you're interested in is where it's 1 and all these decimals going to 0. So this is an occupied to an unoccupied. You want to grab all of those and put them in a new file called OS up. And when you do this, be sure that you physically copy it. You don't just type it in because there's like a weird number of spaces in there. And it's just helpful to inspect OS strength when you do this prep so you can copy the 1s and 0s exactly as they appear in the file. And after you create this OS up, be sure that, like if you do the ls minus lt, be sure that it's not 0 bytes in that file. Because if you did that, then you entered something wrong and it hasn't grabbed any data. So the third code is very similar to the other one, but it's just dipole spin down. Before it was dipole spin up. So this is the other file that you created before. You want to do the exact same thing, except name it OS down. And this is what the oscillator strength looks like. Well, I guess this is the second form. This is OS down, and this is OS strength down. This is 1s and 0s. Actually, I copied the wrong file. Sorry. Yeah, so these are 2 of the same things. Sorry, whoops. But you can use your imagination. This should be a mixture of 1s and 0s. This should be a mixture of 1s and 0s. These are what you want in both cases. So. All right, so combining the transitions. So you need to combine these two oscillator strength files into one file. And as I mentioned before, everything that's oscillator strength up doesn't have that tag saying that it's up at the end, it's just oscillator strength. So you'll want to move that to oscillator strength up and make sure it's gone just by removing it as well. If it's successfully moved, then it'll say this thing doesn't exist. What are you talking about? So now you have a file that was created before that you want to populate with the OS up and OS down that you created before. So you'll concatenate those with these two files. So we do up first and then down, and then they both become oscillator strength. And then the next thing that you want to do is do a word count on oscillator strength and note that number. I think for this, I mentioned that there were 48 states, or 46 states or something, in each oscillator strength up and oscillator strength down. After I concatenated these, the total oscillator strength was like 1,100 different transitions, and that's even after weeding everything out, so there's a lot of transitions in this system. The final thing that you'll want to do is make the spectrum, and it's in the bin. So it'll have many different prompts, so you'll want to be sure that you did the word count before, so you can answer that first question correctly. Then you'll want to enter the minimum and maximum energy. The automatic prompt, I think it's like 0.5 and 3, but if you do that, you'll only get a very, very narrow spectra. So 0.1 and 10 work fine. 0.01 for the line width, that is in the prompt, that works well. They'll also ask you for the highest occupied molecular orbital. And because you have two states, it'll be confusing, because I think in this system one was 26, the other was 29. But Dr. Keelan said it doesn't really matter, you just pick one, it doesn't really affect how the spectra looks. And then there should be some familiar steps, just new plot. There's two different new programs, one for the transition energy in electron volts, and then another to look like a UV vis spectra. So it's nice to do both. Then you'll convert the PS files to PDF and then transfer them to the local box to look at them. So this is for the cobalt tetramine dichloride system that we were looking at. So the transition energy is here, and then you have the UV vis spectra. And here is a picture of a very similar material. It's the same metal, same oxidation state. I think it has one more amine and one fewer chloride, but it's very similar. And if you look at the UV vis spectra, the absorption is very, very low at about 420-ish. And it's hard to see the scale, but I tried to line this up as best as I could. And I guess it's not really, but this is 400, this is 450. And so you'll have a lot of light that's not absorbed in this region. And then there's a lot of things beyond red that are also not absorbed. So you have this part. So if you imagine that color mixed with that color, it's pretty close to the actual material. So it's something that's interesting to get you started thinking about color and transition metals, but it's not totally reliable. I did go back and I changed the number of electrons in the system by modifying the NCAR and then going through all these steps again. And the spectra looked exactly the same, which was sort of troubling because the cool thing about transition metals is they have different numbers of electrons that are stable, and typically those salts are different, so I'd expect the UV vis spectra to be different, but I couldn't really notice any difference in the system. And again, here's the density of states for this spin system next to the transitions between occupied and unoccupied states in the same units. So these two states, well, this very small transition right here, it's probably these two states that nearly overlap, and then everything else that's higher, you could probably trace back what's what, but that's easy just because there's they're so close in energy. So, does anybody have any questions?